All right, so in this video, we're going to talk about phosphines and transition metal phosphines. And though technically speaking, phosphines don't make up organometallic compounds, they have a lot of similar properties to metal carbonyls. And so we lump them together here. The orbital overlap, in particular, the bonding dynamics are quite similar to carbon monoxide. And so you have the same situation where you have a sigma donation that can occur from an occupied MO on the phosphine, and that can donate into the metal. But you can also have pi back bonding from the metal into an empty, it's actually an empty sigma star this time, orbital on the phosphine, and so on the phosphorus. So, this is still called pi back bonding because it still has pi symmetry, even though it came from a sigma star orbital, came from an anti-bonding sigma star in the MO diagram for phosphine, right? It still requires pi type symmetry where two lobes are overlapping, right? One set of lobes and two set of lobes, so it's still pi back bonding. Phosphine itself, pH3, is really a flammable gas. It's poisonous. I think it's reported to smell like cut grass, like a freshly mowed lawn. So it's kind of interesting. I don't think it's related in any way, but that's, the lawn isn't giving off phosphine, but anyway. And so, people don't really use phosphine itself. They use substituted phosphines, but colloquially we call any substituted phosphine with different R groups, PR3, we call them phosphines still. So yeah, you can put all sorts of different R groups here, and that can allow you to control the sterics and electronics of the phosphines. So you can have, something that's not very electronegative, like a methyl group, and so that's going to be a better donating ligand. Or you can have, something that's a little more electronegative, like an aromatic group, or more extreme would be like a fluorine, right? So PF3 is a common ligand that's used. And then there's this concept of cone angle, which is a measure of this cone that's formed, okay, by two of the R groups and the metal. And that gives you an idea of how much steric bulk the phosphine takes up. And so you can come up making this plot where you're looking at the cone angle here in the x-axis, okay, and the stretching frequency of the carbonyl. Now you're saying, well, there are no carbonyls in phosphine. Yeah, I know there's no carbonyls in phosphine. This is the carbonyl. This is now mixed transition metal complex that these are measured on. So you have a metal with a carbonyl bound, at least one carbonyl, and a phosphine. And by putting different phosphines, you can measure the stretching frequency of that carbonyl. Well, the electronics of the phosphine affect the stretching frequency of the carbonyl. So for example, if you have a really highly electron withdrawing phosphine, like phosphorus trifluoride, right? That's gonna have a very high stretching frequency. And why would that be? Because you're pulling a lot of electron density away from the metal center, right? And so as a result, all the electron density of the metal center, a lot of it is going towards the phosphine. And so you don't have a lot of back bonding of the metal donating to the carbonyl, right? Which is what weakens the carbonyl stretching frequency, okay? Refer to the previous video, right? Where we had these carbonyl stretching frequency vibrations, right? Where if we had less pi back bonding, we were more in this sort of situation with the resonance structure. So we had a higher wave number of the carbonyl. So you can use the carbonyl on a transition metal complex in order to gauge the electronics of the phosphine ligand. So PF3 is very electron withdrawing, and thereby is not allowing metal donation. It's taking electron density away from the metal. It's not allowing metal donation to the adjacent carbonyl, okay, that's also coordinated to the metal. So very interesting. And so you can now tune your reactivity, right? So you can say, oh, I want something that's really sterically bulky and also electron drawn. Well, I better use these, benzene rings that are perfluorinated. They have this fluorinated. Or, I want something that's just really electron donating, you know, and bulky or something in between, right? Because bulky ligands can also control steric number and coordination, right? If you're using really bulky phosphine, probably you're going to favor a low coordination number because you can't put a lot of these ligands around around a metal center. So there's a lot of tricks you can play that organometallic chemists use. You can also use chirophosphine ligands, and these are used extensively on an industrial scale to make different compounds. So here's one of the more common compounds, but these are chiral, okay? And so what you can then use these for is once you have the chiral phosphine ligands, you can use it to direct catalysis to make other compounds, like I said, for a lot of times for industrial purposes, olefin metathesis, things like this, making different polymers. There's all sorts of catalysts, small molecules. But you can induce now chirality into those molecules that starts from the chirality imparted in these phosphine ligands. And so, you know, asymmetric catalysis, something I'm not an expert on, but a field I definitely find fascinating and really interesting. All right, so that's the overview on phosphine ligands in organometallic chemistry.